Hello, everyone. I'm sorry there was a technical problem with we had some delay with the live stream. Anyhow, thank you very much for being with us today. My name is Giacomo Beccari, and I would like to welcome you to the new event of the ESO Cosmic Duologue. I would like immediately thank Stefano, Ted, and Morbi for accepting our invitation, for organizing this event. Thank you so much. And of course, this is a very, very exciting topic. We will hear a dialogue about the structure, substructure actually, so the gaps and rings were found in protoplanetary disks. This beautiful new result that we got observationally, and we will discover and we will learn what they are, what about them. I'm really looking forward for this. Just to give you the usual general technicalities. So this is a professional, this is a series meant for professional astronomers, and everyone is very welcome to make questions. You can both do it using the live chat, which is available on our YouTube channel, or if you prefer, you can also send your question using the dedicated form that you can find on our webpage, duo.eso.org, or you can also send an email at esoduo2020@eso.org, and we are monitoring in real time the email, so we will also pass the information and then your question to the chair of the session. So this is the fifth event. There will be two more to come. I think this is all about the technical parts, and then of course the video will stay online, so you can see the video again in the future. And also don't forget that we have put all the live events on our pages for all the previous talks, and you will so you will be able to see them. And also we collected the most relevant questions on a brochure that you can find in PDF form on our web pages, where you can see the questions with the major answer from the previous speaker. So this is also material that you can have a look at. And finally, just to give the structure. So now the chair will give a very short introduction. There will be the two speakers. They will give 20 minutes talk each. And then at the end, the dialogue will start. And as I said, everyone is always very welcome to participate through the live chat. With this, I will stop sharing my screen, and I will disappear, and I will leave you the stage to Stefano. Thank you, and enjoy the event.
So thank you, Giacomo, and Harry as well, for the organization of this new ESO Duologue. And as you can see in the slide, today we're going to talk about the substructure in protoplanetary disks, a signpost of planet formation. And this duologue follows up another event we had a few weeks ago, where we focused mostly on the formation of our own solar system. But today, in particular, we'll extend our view and focus on the planet formation in the whole solar neighborhood. And this duologue is observationally motivated by the fact that, sorry. The slides are stuck. Here I am. Observationally motivated by the fact that since 20 years or so, observations of circumstellar material, in particular protoplanetary disks, have started to show substructures when imaged at high enough angular resolution. These images are about between 0.2 and let's say 0.5 arcsecond resolution with different instruments, ranging from HST in the scatter light to Plateau de Breux in the center, and ALMA in the very early stages on the right. And when imaged at this resolution, bright objects start to show some level of structure in both the radial and azimuthal direction. But a few years later, in particular 5 years ago, the ALMA long baselines science verification campaign obtained this iconical image right now of the famous HL Tau disk, where this object, which is fairly young, shows and presents a series of rings and gaps. Here I'm showing what is the millimeter emission of this circumstellar material for this particular star. And the tremendous advancement in the angular resolution, both with the ALMA long baselength campaign and with advancement in the adaptive optics on ground-based telescopes, in the next years showed a plethora of spectacular images of protoplanetary disk, of possibly planet hosting, planet forming disks. And here we can see images from ALMA, and the bottom right 3 panels show images from Scatterlight. In particular, these are, if I remember correctly, Sphere and GPI images. So the question today is, what are these rings and gaps, which are probably the most common feature we see in these object stellas? Are they signposts of planet formation? Are they the signatures of embedded planet that are sculpting their natal environment, or they're due to other physical mechanisms? And to try answer this question, this major question in today's astrophysics, we have 2 speakers today, which I really thank for being able to join. And let me stop the sharing in the meantime. And the first speaker that we have today is Ted Bergin. Thank you for being here, Ted. Ted had his PhD from University of Michigan in '95, and then stayed as astronomer and astrophysicist at the Smithsonian Astrophysical Observatory in Cambridge in the US. And then moved to the University of Michigan, where he still is now as chair of the Department of Astronomy. And the contribution of Ted to the star and planet formation field are really numerous, in particular focusing on the ISM. Again, star and planet formation, both from the theoretical and the observational side, with a particular focus on the astrochemistry side. And in terms of observations, for example, he has been PI of the Hexus key program with Herschel, and is currently co-PI of the ALMA MAPS large program. And Ted has also received several prizes, for example, the Harry Russell Award from the University of Michigan and the Danny Heinemann Prize last year for his pioneering work in astrochemistry. So thanks, Ted, for being with us. And the second speaker, Alessandro Morbidelli, worldwide known as Morbi. Morbi graduated in Milan, then moved to Belgium to the FUNDP University for a PhD in mathematics. Then moved to France, where he's now director of research in the in astronomy in Nice at the CNRS at the Observatory de la Côte d'Azur. And also Ted's contributions to the planet formation field are outstanding. He's an expert on celestial mechanics, on the formation of the solar system, and in particular is one of, let's call them, founding fathers of the formation of our own solar system from with the so-called NIS and then relabeled Grand TAC model. And also Morbi has received several prizes, for example, the bronze and last year the silver medal from the CNRS, and is an elected member of the Academy of Sciences, Belgium and France. So thanks, Morbi, for being here. And with this introduction, I'll give the stage to the floor to Ted. So as Giacomo mentioned, we have 2 talks, 20 minutes each, first by Ted and then by Morbi. And after that, we'll start our dialogue, and I'll ask any questions that will come up in the chat to the speakers, and we'll have roughly 40 more minutes of dialogue after the talks. So we can start with the first, and thank you again both for being here with us today.
Okay, so first, before I get started, we're all set? Everything, you can see everything?
Yeah, I can see it.
All right, well, thank you. It's a pleasure to be here and participate in this discussion in a very exciting time in the study of the birth of planets. Before I get started, I have to acknowledge that just a tiny portion of the work that I'll show here today is from myself and my group, and I want to acknowledge my sponsors that fund this science, the National Science Foundation and NASA. And in particular, I have to call out, I'll be talking a lot about observations that come from this observatory here, the Atacama Large Millimeter Array, which is a joint project funded by Europe through the European Southern Observatory, Japan through the National Institute of Natural Sciences, and in the United States through the National Science Foundation. This is our duologue here, the structure of planetary disks, a signpost of planet formation, ? And I want to hold up this side of the debate that what we're seeing are signposts of incipient and active planet formation. First, the obvious, and I'm certain that Morby would agree with me. Here's pictures of two giant planets from our own solar system, Jupiter and Saturn. You can also see evidence of two moons as well. The giant planets form where the gas is present, and we are observing the gas-rich stages that are basically commensurate with when we think giant planets are being born. They have to be born when the gas is present. There are some planets here, so the question is, how many? And is everything that we're seeing evidence of planet formation? And here is the exoplanet statistics as circa a couple years ago. Here's planet mass versus semi-major axis, and you can observe the color coding is the different techniques via which planets are detected. And the scales that we're looking at in the images that I'll show you are out here at greater than 10 AU. And in particular, we're very nicely sampling this regime here where we're seeing these Jupiter mass or larger mass planets at large distances from the star. But there's a vast territory here below the Jupiter mass that is unprobed currently by current exoplanet detection techniques. And this also is the parameter space that we'll be looking at today. In terms of looking for planets around this, there's a bunch of ways that one can do it. In particular, what I'll focus on here is a giant planet carving a gap in the disk, and that gap exists both in the solids and in the gas. And behind that gap on the edges, you have what we call a ring, and this ring is where the dust grains, the solids are piling up, and perhaps is the foster site for the next round of planetary assembly. Another way to do it is actually detect the emission from the protoplanet itself, either through the disk that surrounds the material or from the accretion onto the planet. I'm going to focus on the results from the Atacama Array, which are tracing the mid-plane of the planet-forming disk, and for the most part, tracing about millimeter-sized pebbles that are in that planet-forming mid-plane. But we have to acknowledge that there's the other way to approach this, and that is to actually detect a young planet itself. And the very exciting result here that I'm showing here from the VLT sphere is the detection of a protoplanet in the source PDS-70. Here's the disk. There's an evacuation of material in this region here. There's a planet here. We also think there's likely another planet in this system here. And what you're seeing here is the scattered light off the surface of this disk. And this right here is a detection of H-alpha emission from an accreting protoplanet. So this is a direct way to detect planets, but it's very hard to do. There's a number of reasons why this is. One may be to do with how planets are assembled. We're not certain whether planets are born and how the energy is released as part of that birth. And so there's the so-called hot start versus cold start models, and it's harder to detect the planets that are colder. It may be that the accretion onto the planet itself is episodic in nature, so we can't capture, say, this H-alpha emission all the time. And it's also the case that directly detecting planets below the mass of Jupiter is very difficult. And that's at these large distances. Of course, we have directly detected many planets less mass than Jupiter close to the star via other techniques. So this is the landscape we're looking at. This is the results from the D-SHARP program from AMA. So these papers that have the summary of this from Sean Andrews and from Jane Huang. And what you want to see here is, here's the scale bar here. This is 10 AU scale. This is the resolution element. And I'll just let this sort of run. You see beautiful structures, lots of prevalence of darker regions, these gaps, and brighter regions outside of the gaps that we call rings. And an interpretation of this is that all the gaps are caused by giant planets that are carving the gaps, or maybe super Earth or mini Neptune planets that are carving the gaps. And that's summarized here in the results from Zhang et al. 2018, where they modeled the gaps. And these are the planets that are inferred to be present. And you want to notice that there's only one planet up here that's commensurate with where the detection statistics from direct detection are clearly associated. And most of these planets are occupying a sort of a new terrain, not entirely new, right? We have Uranus and Neptune and Saturn in our system, but they're implying the birth of planets that are commensurate with Uranus, Neptune, Saturnian sizes at larger distances. And again, that's the maximal interpretation in a way that these rings are equal to planets. And so how does this work? There's a whole large industry about this, where people are using hydrodynamical models of both the solids and the gas. And this is just one example from Fouché et al. 2010. There's many others. I just list a sampling of this wonderful, wonderful work. There's a great interplay today between the observations and the dynamics that is constraining the evidence for planets in these systems. So what you're showing here, this is the surface density of either the solids or the gas versus distance. And it's a planet placed here at this position on the order of like 30 to 40 AU. And the different size planet is put into the system, 0.1 Jupiter masses all the way up to 5 Jupiter masses. So 0.1 is this green line here, and the 5 is the solid white line. And you can observe that as you put a planet into the hydrodynamical model, that a gap is carved, and that the size of the gap, the width and the depth of the gap in the millimeter grains is larger. And you see a same sort of thing in the gas happening, but it's slightly lesser, a lower effect in the gas, okay? So the gap width depends upon the math, the depth as well, and you can trace it both in the dust and also in the gas, but it's slightly easier in the dust. So this is an example of that. This is a work from Masella in 2016. Showing the image of the HT 163-296 disk. So again, we're looking at the emission of the solids in the disk, the millimeter size grains. This is the thermal continuum emission from these grains that are essentially reprocessed starlight. And these structures you hear, the gaps are in the dark, and the ring here are the brighter areas. And in this particular model, they infer the presence of 3 planets that are in the order of slightly less than a Jupiter size body. And this work was notable because they modeled also the dust and also the gas as traced by CO emission. Now, I take a step back. The dust we can trace directly, and we're very sensitive to the emission from the dust. The gas is a little bit more difficult to probe because we have to zoom into a smaller region of the the wavelength space, and we have less sensitivity. And further, we are not directly sensitive to the most abundant gas, that is H2, and we have to use alternative probes, in this case, the emission from carbon monoxide, which is what is probed here, or shown here, to trace the H2 itself. So here's another example. This is the AS209 disk. This is from Guzman et al. 2018. And this is a neat system. So what you see here is the surface brightness of the disk, shows a function of radius, and the gray is the structure that you see in the millimeter emission. And it was noted earlier that if you take a disk where there's sort of lower turbulence or low viscosity, that a smaller mass planet could induce perhaps multiple gaps. That is, you can have multiple gap systems caused just by one planet. And here is an example of a model of a 0.1 Jupiter mass system. This is from this paper here, Zhang et al. 2018, but we have to acknowledge a lot of the great earlier work here. And you can see that you put a Jupiter mass planet here at 100 AU, and you can induce a gap here at 60 AU, another one at 40, and even a third one closer in. However, there's something else inducing something here, right? So not only is it evidence that, you know, a planet carves a gap, that's the case, but it may be the case that you don't need to have every planet, every gap, I'm sorry, being caused by a planet. Now, this is tricky, as is everything in astronomy. The way we get at the dust surface density here to compare to the hydrodynamic models is take the dust emission that we observe, and we have a factor here that sort of encapsulate the dust optical properties. That depends upon how the dust is, how we model the dust essentially depends upon our assumptions. And as the dust grains grow, this number here, this correction factor, if you will, can change. And of course, we don't know a priori what the dust is doing in its entirety. If grains grow to greater than centimeter sizes, we cannot trace them via this emission. They're essentially unprobed by AMA. So this means this parameter could change as a function of position in the disk, and that could complicate our interpretation. Nice paper by Panilla and Uden that sort of shows that. And the gas surface density, again, I said we trace it from CO emission, and that depends upon the abundance of CO. And there's a lot of work as well that's showing how the abundance of CO can be altered as well, and that may be to position dependent. And this actually all the way goes back to Yuri Akawa's work in 1996, showing how ionization can alter the abundance of 12CO or carbon monoxide in disk systems. So it'd be nice if we could have another way to approach this, and that is coming through the dynamics. And there's two ways that individuals have approached this, various two groups. And one is by using deviations generically from the rotation curve, and the other is spatial independent, another is localized. So I'll talk about each in turn. So what you're looking at here, this is the HD163 disk again, but now I'm showing the 12CO velocity field in this beautiful, beautiful image also from the D-sharp results. You could even see the disk cusping up and the flaring of the CO surface. This rotation velocity you see here has different terms. One depends upon the Keplerian velocity field induced by the stellar mass, and that depends upon the radius and the height at which the emission is being traced by CO. But there's also a term that depends upon the gas pressure gradient, which there's a radial gas pressure gradient decaying outwards as you go to larger distances. And Rich Teague has modeled this along with Shaihan Bey. And what you see here, this is the 12CO, again, the velocity field. This is a fit showing where the surface of the emission is. And the beauty of ALMA in some of these disks is they're flared enough that you can actually resolve the height at which a given tracer is emitting from. And this is a fit to that surface. And you can see that, you know, you're out here At this distance, it's a height of about 75 AU, and that's at an order of like, say, 200 AU or so in distance. So why does this matter? That is, this term here, this radial pressure gradient term, has this radius term. I can easily measure that, but you can also account for the height. And so that means if we can measure this rotation velocity with great precision, we might be able to get at the gas pressure gradient from the velocity itself. And why does that matter? That matters because now we're tracing H2 directly. It's the H2 gas pressure, and this is independent of anything that's going on with the abundance of CO, which is our tracer here, but we're tracing the H2 pressure directly. So what would happen in a gap caused by a planet? You would have a minimum of the gas pressure, right? So in the center of the gap. And as you go down here, you would have a minimum of the dPdr, the change in the pressure, and then the pressure would start to rise as you go to the outer edge of the gap. If you were to look at that in velocity space, what you would have is you'd have a negative velocity signature and then a positive velocity signature across the gap. So here is the rotation velocity from this, in this case, it's in the 2019 paper by Rich Jahan and myself. And you could see the radial gradient here, and these velocities are done in this case by spherically averaging, so you get improved precision. And so these little bumps and wiggles that you sort of see here, they're actually real. And so this is the change in that velocity gradient, if you will, basically fitting this by the Keplerian rotation and subtracting it out. And there's a gap here, a gap here, a gap here, another gap here, and you can see in the presence of the gap, there's this signature here of the pressure gradient rising. So what this means is we're using 12CO, and 12CO was an imperfect probe for what's going on directly with the H2 because of this possibility that its abundance is changing. And we have now confirmed that the gas pressure is indeed dropping in the center of the gaps. And that is, again, consistent with a giant planet carving out the gap in the system. And these were modeled actually by Jahan Bay and fit with sort of Jupiter-massed planets carving these gaps. Now, another way to approach this, again, using kinematics, is much more localized in action. And this is work by Christoph Pint in 2018. So this again is the HD 163 disk. This is the dust thermal continuum emission. And here is the 12CO. In this case, we're zooming in and looking at just one velocity in the disk. The spectra that you obtain with ALMA for the molecular spectra are velocity resolved. And so we can look at specific velocities in the system. And what you're seeing here, actually, and this is when I told you can measure the height at what something is emitting, here is the front surface of the disk. There is the back surface of the disk. And this dark space in between is the actual disk material. The reason why it is dark here is because the CO is frozen on grains in the midplane at these distances. And there is a radial or vertical temperature gradient that when you get to high enough heights, it gets hot enough and you release the CO, and that's why you can see the CO emitting at the front surface and the back surface of the disk. And so that's, in a way, chemistry being seen with your own eyes. So this is what the normal Keplerian velocity field would look like. And what Pint et al. Noticed is that on this side of the disk, all of a sudden, there's this kink in the system. And they were able to model this by putting a planet in the midplane, right here, where inside the midplane is where the CO is frozen, all right? And it is inducing a kink in the velocity structure at those heights. And so this is the idea that you have a planet, and this is, again, another hydrodynamic model, again, from that paper. And induces, in this case, there's spirals, but what you're looking at here is this is the rotation of the planet. And if you want to think about it this way, it's the wake of the planet inducing upon the gaseous material in the surrounding disk. And so what we're picking up here is essentially the change in velocity induced by the planetary wake. So this is the model. So again, this is our just one velocity channel. And the neat thing here again is this is localized in space. So there's, the planet is in one spot of this disk. And here's a model, again, linking hydrodynamic model, modeling and predicting what ALMA observations would look like. This is a Jupiter mass planet, 2 Jupiter mass, 3, and I think, I'm sorry, this is 4, but I believe this is 5. So what you observe here is, 1 Jupiter mass doesn't seem to be enough, 2 seems to be a pretty good fit, and 5 seems to perhaps be a little excessive. So they model this and claim the detection of a 2 Jupiter mass planet. A more recent paper by Christoph Pint and his collaborators analyzed the D-sharp data, the molecular CO data that I didn't show, and they find 9 localized velocity disturbances in 6 systems, all right? And these localized disturbances can coincide with gaps and could be interpreted, therefore, as the direct evidence of planets inside each of those gaps. And I want to also call out the very nice work by Casousis and Perez, 2019, a number of papers by these authors. They also note the possibility of detecting planets via the kinematics by looking at essentially trying to detect the wake and its change on the Doppler, the localized motions in the disk. Okay. The last kinematical evidence for the presence of planets is actually in the 3D velocity field that Rich Teague was able to tease out, again, using the D-sharp 12CO data. And here, what you're able to actually estimate is the 3D velocity field, both height, radius, and also azimuthal. And this is just showing one set of components here. This is height versus radius, also in the HD163 disk. These red areas are where the gaps are, and the blue area here is the outer edge of the disk. So this is the area where Christoph Pint's directly detected planet is claimed to exist, or indirectly detected planet, I'm sorry, inferred from velocity. And what we observe is that the gas is actually infalling into the gap here. So what's happening is in this area, the gas is flowing this way and then falling into the gap. Same thing here. And the same is happening every place where we have evidence for either a gap, in this case, a gap in the dust, and this is a gap in the gas. And again, this is the kinematically detected or inferred planet, and this is the inferred planets, both from the gas and the dust and the kinematics. And neatly enough, in the outer edge of this, we see these vectors turning around, evidence of a flow going outwards, which may be a wind. And the length of the vectors here is telling you something about the magnitude of the motions. And that's what this scale shows here. Now, what do we think we're seeing here? We believe we're detecting a predicted flow that is induced by the presence of the planets, so-called meridional or circulation flow. That is, you have a planet here in the disk and the gas flows like this around the planet, and there's a bunch of papers detailing this, including by my esteemed co-debater here. And the 12CO emission is coming from the surface of the disk, and so we're only picking up the gas flowing in to the system. And we hope, as we get better data deeper in the disk, we may be able to detect changes in the flow, or maybe even the reversal in the flow, and further constrain the kinematics induced by planets. So where are we today? Right now, the case for planets is clearly strongest in HD 163296. I will note that there is a mismatch between the planet mass estimates from the dust surface density and those inferred from the dynamics, and that the dynamical masses of the planets, by matching 2D or 3D hydro simulations to the gas kinematics, give masses that are a factor of a few to even perhaps sometimes 10 times higher. And this was noted by Christoph in his work, but also by Rich T's work in 2018. There's a really neat paper that I encourage everyone also to look at by Lodato 2019, who looks at the fate of these planets and suggesting that the planets that we infer to be present from the D-sharp data and also by these kinematical data will likely migrate inward. If we want to think about statistics and understand, you know, the exoplanet statistics, are we in any way in conflict with current exoplanet statistics? And we have to note that the D-sharp has a very high occurrence rate. They detect rings and gaps in many systems. Here's a plot of the effective radius versus the millimeter flux normalized at 140 parsecs from Long et al. 2020. Here's the D-sharp data, and this is just some of the other surveys, not all the other surveys, showing that the D-sharp data, not surprisingly, they were selected to be the brightest systems, the ones that are easiest to probe in this pioneering study to look for the prevalence of structure. You would start with the brightest systems, but obviously they are the brightest systems, and so they may not be representative of the population. To look at that, you can go to the Taurus survey by Long et al. 2018. This is a different Long. The previous one was Darrow Long. This is Feng Long. And that survey, the Taurus surveys, finds a 38% occurrence rate, slightly smaller. Now there may be more structure inside the resolution limit, but let's just assume that. And this is summarized in a very nice paper by Fernandez et al. 2019. The disk frequency in Taurus is 75%, so the full occurrence rate would be 28%. And you can look at the giant planet occurrence rate. So this is from 1 to 100 AU. From these masses, that's about 26%. And I talked to my colleague Mike Meyer, and he also gives me another occurrence rate from this case 0.1 to 1,000 AU. It's about 21%. And so these are sort of commensurate with the numbers that you get from the rings. And so the occurrence rate are consistent, provided each source has one ring, right? But many sources have more than one rings. So that may hint that we're seeing something different. What that something different could be is that single planets could induce multiple rings. Another possibility is that you could have small mass planets, less than a 0.1 Jupiter mass, which are not currently easily probed with any survey and have to be inferred. And in low viscosity disks, these have been shown to be the source of rings, such as in TW Hydra by the Mentaplay and by other work. But we also have to say that the dynamical mass estimates would claim that the masses have to be higher. So can we get concurrence with low mass planets and the dynamics? That may be difficult to know. Another possibility, of course, is what you'll hear from Morby, is that each of these rings is not due to planets, and many of them could be due to something else. But there are planets there. So here we are. Our current ALMA data sets have been optimized for dust continuum. They have not been optimized for gas kinematics. We need many more hours, so there's an urgent need for that data to push this field further. We obviously have looked at the brightest disk. We have to go and see if we can tease out structure in smaller disks. And that requires sort of super resolution techniques, such as shown in this paper here by Zhang et al. 2016. I have not talked about the amazing works from GPI and Sphere. And so I encourage everyone to follow up on that literature. And here's one example of a very beautiful paper. The possibility exists to look for chemical signatures. And we have, this was in a paper by Ilse Cleves in 2015. We have a new ALMA large program, the Chemistry of Planet Formation, going by the acronym of MAPS, Molecules at Planet Forming Scales. That will search for these signatures and provide some of the better data for kinematics. For example, we should be able to look deeper in HD 163. Planets are there. And we also need to find them and confirm some of the ones that we have detected by inference to help us know whether we're right or we're wrong. And I'll leave you with a picture of some of the data from the Molecules at Planet Forming Scales program, the MAPS program. These are just a sample of images from one of our desks. Each of these is a different molecule or a different molecular line. And you can observe the beautiful structure that we see in that emission that is telling us something about incipient planet formation occurring today in these systems. Thank you very much. And I will stop there and stop my screen sharing.
Thank you, Ted, for the great talk. Before I won't ask any of the many questions I have right now, and I'll pass the floor to Morbi.
Okay, thank you very much. Can you see my screen?
Yeah, I can see it.
Okay, let me go in presentation mode. Okay, so thank you very much for the invitation. Hello to everybody attending this duologue. So you have understood the duologues of ESO want to be on some controversy in order to echo the famous dialogue of the two chief world systems of Galileo. So Ted is enacting Galileo today. I'm enacting Simplicio. So I'm trying to counter argument what Ted say, and explain to you why I don't think that most rings are due to planets. And I, of course, agree that some planets must be there and some rings may be due to planets, but probably not most. And the outline of my presentation is this one. I'm a theorist, so we start from theory, right? If we want to have planets at 100 AU, which is the typical distance where we observe these rings and gaps, well, it's awfully difficult. I will explain you why briefly. Then I will go through the list of arguments that seems to demonstrate that there are planets there and show some counter arguments, and then we can debate. Then I will talk about alternative mechanisms for ring formation that can explain what we observe, and then of course some conclusions. So if you want these gaps and rings to be formed, to be induced by planet formation, you need to understand how a planet can form. And there are two models to understand the formation of big planets. One is core accretion, the other one is gravitational instability. In core accretion, as the name says, you need first to form a massive solid core of many Earth masses. Then this solid core can start to accrete some gas. The question is how to form this solid core. And there are two competing models, even though they can work also in conjunction. So a core of a planet can form by accreting planetesimals. So you have many other objects, big and small, 100 kilometers, 10 kilometers, and so on. They are in the disk, they collide with each other. Sometimes they break. Sometimes if they fall on a bigger object, they are accreted by the gravity. And so the object can keep growing. It's what is called oligarchic growth. And then there is the other mechanism, which is pebble accretion. The forming planet is embedded in a disk of gas and dust. The dust drifts towards the central star because it's dragged by the gas. And by doing so, it goes through the planet orbit, and part of it is accreted by the planet. So the planet grows by accreting dust particles. Now, this mechanism of formation works relatively close to the star, and far from the star, it's quantitatively more difficult. So if you focus on planet formation first, the efficiency of planetesimal accretion first, the efficiency of planetesimal accretion depends on the mass density of planetesimal, which is expected to fall further away from the star, on the orbital frequency, which is expected certainly falls as you go away from the star, product, but also depends on this. This is called the Safronov number. This is the squared of this ratio, which is the escape velocity from the surface of the growing planet and the orbital velocity at the location where the planet is trying to grow. So if you have a planet of a given mass, V escape is the same, wherever the planet is, close to the star or far from the star. But the orbital velocity decays. If you are further from the star, of course, it's smaller, so this ratio is bigger. And when the Safronov number is bigger than 1, so if you are far enough from the star for a given mass planet, then dispersion wins over accretion. What does it mean? It means what you see over here, if I remove Stefano from my slide. So the planet, when it's small, so the Safronov number is small, accretes planetesimal in its neighborhood. But once the planet starts to be massive enough, and the Safronov number becomes bigger than 1, the planet starts to scatter the planetesimals away rather than accreting them, eject them from the system. And so the accretion becomes very inefficient. And this is known since many years ago, Eden Makino, 1993. And for this reason, this problem already occurs for the core of Jupiter at 5 AU. And this is why the concept of pebble accretion has been used. Pebble accretion becomes also very inefficient if you go away from the star, because pebble accretion, the efficiency, it depends on the density, surface density of pebbles, which should decay as 1 over square root of r if you have a steady state flux. Again, the orbital frequency, which decays with the distance from the star, divided by the scale height of the pebble. And because disks are typically flared, well, should be flared as well. So everything, this product should decay as 1 over r to a power larger than 2. So for instance, I did recently in a paper this exercise. I took one of the rings observed in the D-sharp survey modeled by Dulmon et al. In 2018. I took B77, one of the rings. It looks more or less typical. And I used the parameters deduced there. So the surface density of pebbles is low because we are at 75 AU from the central star. So the surface density of pebbles is only 0.2 grams per square centimeters. And various arguments argue that the scale height of the pebbles is 0.028 AU. And no, this is the aspect ratio, sorry. The aspect ratio for the gas is 10%. The aspect ratio for the dust is 2.8%. And the dust is relatively small, so the Stokes number is 3, 10 to minus 3. Well, these are observational parameters. And then I simulated how a planet can grow over time in such a disk, in such an environment. And so if I start with a Mars mass seed and I keep the disk fixed, so no parameters are changing over time, the planet grows, but grows very slowly. It takes 3 million years to reach 1 Earth mass. And this is because essentially sigma pebble is so low and H pebble is so big. And typically disks last only a few million years, but it's worse than that. You see here that in order to have some appreciable growth, I have to start already with a sort of planet, a Mars mass planet. How this Mars mass planet could have grown, it should have grown by planetesimal collision, and that's the problem that I was mentioning. Also, because we are far out, so we are not so far from the outer edge of the disk, it's expected that the pebbles don't flux through the planet's orbit forever. It has been estimated, for instance, in 2016, that the flux of pebble is very short-lived. And for instance, if you have a disk with an outer edge at 100 AU, the flux of pebbles just lasts for 200,000 years. So the typical D-sharp rings are a few hundred AU. So say 400 AU. So this becomes about 1 million years. So this simulation is optimistic in many ways. I leave the disk alive if a flux of pebbles going for too long. I already start from a big seed, which is problematic to form. So even pebble accretion is often invoked as the solution of all the problems, is problematic so far from the start. So maybe one could say these planets don't form by core accretion. Finally, the planets, the long search planets that form by gravitational instability. Gravitational instability is totally different. It's just the gas that becomes gravitationally unstable by itself. There is no need to form a solid core. So none of the problems I discussed before would apply in this case. Gravitational instability has been studied for a long time. And it's now clear that indeed, if it has a chance to happen, it has can happen very far from the star. It still needs a relatively massive disk. So for instance, at 100 AU, we need the disks of about 30 grams per cubic centimeter per square centimeter. It's a typo in hydrogen. And we also need that the disk is cooling very rapidly. The cooling time has to be short, of the order of half an orbital period, because otherwise this clump cannot contract and are destroyed by the shear in the disk. Provided you have these two conditions, then you can indeed form clumps of gas bound by gravity, so by gravitational instability. But these planets are typically giant planets, even more massive than Jupiter. So these are much more massive than those usually invoked to explain these gaps. But maybe they are more in line with those invoked by Pent et al. as Ted said before, I will come back to this. If each gap were due to a planet more massive than Jupiter, I think this would raise a number of problems that, as I will discuss later. So now let's see the arguments that have been brought in order to defend the idea that the gaps are due to the presence of planet, and see some counter arguments. So one argument that Ted did not detail too much, but I liked a lot when it was published, is that a planet can open not one gap, but multiple gaps. So when you see a disk with many gaps and many rings, you don't have to invoke one planet per ring, which is a sort of silly, but one planet can explain the entire structure. And this is extremely powerful in terms of Occam razor. If you can have many gaps coinciding with what a single planet would do, this is extremely powerful. And indeed, this is the focus of the paper by Zhang et al. In 2018, which is a great paper. I would point out, though, that the work by Zhang et al. Is absolutely correct, and simulations are correct. This happens, as Ted said, when you have a planet embedded in a disk which has a very low viscosity. But the simulations have been done assuming that the planet is fixed for simplicity, and also simulating the disk in 2 dimensions. And then things are gentle and easy, and indeed it's true that the planet can open multiple gaps. But if you let the planet migrate, for instance, things become more difficult. So this plot is taken from a recent paper by Kanagawa et al. This year, and shows the structure of the density of the gas opened by the same planet, so a planet which is 30 Earth masses, migrating at different speeds. So as you can see, the planet is placed here at 1. So if the planet is migrating slowly, that's the red curve, you see the main gap produced by the presence of the planet, and then, for instance, a secondary gap, which is quite pronounced, not as pronounced as the main gap, but significant inwards of the orbit of the planet. But if the planet is migrating faster, so for instance, its radius decay by 4 10 to minus 4 per orbital period, then it's the black curve, and then you see that the secondary gap becomes very shallow. It's less than a 10% effect, and it becomes shallower and shallower as the migration speeds up. If you go, and this is all in 2D simulations. If you go to 3D simulations, things become even more difficult. So this is an image, a plot, a simulation showing the density of gas. In the case you have a Jupiter mass planet, so a giant planet in a disk of gas, very low viscosity, simulated in 2D. So the planet is here in the main gap, which is totally devoid of gas, so the black ring. But then you see that inside the orbit of the planet, you see several concentric rings, which are open by Jupiter, even if the planet is here. This is the same simulation, same disk, same parameters, same boundary conditions, but done in 3D. So Jupiter is here, you see the main gap, but then in the inner disk, you don't have multiple rings, you just have a unique structure where the density of gas increases, reaches a peak here, and then decays towards the star. So it's not so clear that the planet can open multiple gaps in realistic simulations conducted in 3D, and maybe even accounting for migration. Then you have this work, this meridional circulation that has been detected, the Teague paper in Nature. This is fantastic work. It's really science fiction made real, and I'm blown away by these results. What do they show? So they show that there is a meridional circulation like this. The gas in the surface at some region falls towards the mid-plane and then goes away. And certainly a planet can do this kind of circulation. But why is this circulation happening? This circulation is happening for a very simple reason. There is some mechanism, in this case a planet, that tends to remove gas from the mid-plane. But the vertical structure of the disk is dictated by hydrostatic equilibrium. So as soon as you have a mechanism depleting the disk on the mid-plane, then you have to have surface gas falling towards the mid-plane because it's not sustained by hydrostatic equilibrium anymore. So this kind of meridional circulation, you can see them wherever you have a mechanism removing gas preferentially from the mid-plane as opposed to from the surface of the disk. Then you would have the same kind of gas circulation. A planet can do it, but as we will see, it's not only a planet that can do this. Then you have these velocity kinks. Ted also spoke about this, and these are maybe stronger evidence because it's really discontinuity in the velocity of the gas. And so for instance, you need some perturbance in the disk, which is localized in azimuth. So a planet is really, but in this fantastic work by Christoph Pent and collaborators, they find hints for velocity kinks, so for planets, in 8 out of the 18 disks, which have been imaged with rings and gaps, and each disk has more rings and gaps than one. So it's only 8 out of many. And so they don't find evidence for planets in every gap, in every ring. And it's very strong also one should underline that when they find evidence for a planet due to the velocity kink, this planet falls in a gap. So it can be the origin of the gap, but not all gaps and rings, not for all gaps and rings, they find a planet candidate. So if real, these kinks, and so due to the planets that can induce them have to be very massive, more massive than Jupiter, 2-3 Jupiter masses, so typically more massive than those deduced, for instance, by looking at gap morphology or meridional circulation, as Ted said. It's unclear to me, it has not been discussed in the Pent et al. Paper, it would be worth to look, is whether these massive multi-Jovian planets can actually open gaps or would rather open cavities in the dust distribution. Because if to open gaps, you need to modulate the dust drift speed, but the dust must be able to pass through the orbit of the planet. If the planet is too big, then the planet opens a barrier. And then the dust accumulates outside of the orbit of the planet and cannot go through the orbit of the planet. In that case, you don't open a gap in the ring, you open a cavity. You keep all your dust outside the orbit of the planet, and the inner part of the disk becomes devoided of dust. We see many of these disks, they are called transition disks. So, and this depends on the scale height of the disk of gas versus the heliosphere of the planet. And 2-3 of Jupiter masses are pretty big. And even if the disk has a scale height of 10%, it's not clear to me that they will not open a cavity rather than a gap. But I never did the calculation personally, but it's worth to check. An issue about these planets, if they are real, is aren't they too many? Like Ted said, there are many disks, all the extended disks that we see have many rings and gaps. Which are the ring and gap, or many of these rings and gaps are due to planets. There are a large number of planets out there. So this diagram has been shown already by Ted from Zhang et al. Shows the planet location and masses as deduced by reconstructing the morphology of the gap. These vertical arrows I put here is to show that 4 of these planets are found by Pent et al. As well, but the masses, instead of being sub-Jovian of order of a 10th for Jupiter mass, is 2-3 Jovian masses. So there's a big uncertainty on the masses. So if Pent is right, and these planets are very massive, then the planets that we see in the disks are directly comparable with the planets that we see by direct imaging once the disk has disappeared. And these planets seen by ALMA or GPI are fairly rare. That's why ALMA and GPI didn't find many of them. And instead, 8 planets in 18 disks, it's quite a lot. So Pent et al. Already discussed this discrepancy. They argue that, well, maybe these planets are just small enough not to be seen, or maybe the planets don't stay bright and hot long enough to be easily observed by direct imaging. So there are a number of ways to reconcile the problem, but certainly it's a problem to be considered. The other possibility is that these planets are not as big as Pent et al., are rather small, more comparable to what predicts. So these planets clearly, if they stay here, would not be visible by direct imaging. And interpretation is that these planets would continue to grow, and as they grow, they migrate. And as, for instance, the Lodato paper that Ted quoted before. And so these planets are just the precursors, not of the giant planets that we see today by direct imaging, but are the precursors of the warm Jupiters that we find by radial velocity measurements or by tracking. And of course, these are much more numerous than these ones. These ones occur very, very rarely around stars. These occur around 10% of the stars or 20% of the stars. So the numbers become more reasonable. It's the comparison that Ted did before, this 20-25% occurrence rate that Ted debated. My point here is that if this is true, that these are just planets that will migrate here and will grow and migrate, then we would expect to see that this distribution of gaps and rings change with the disk age. And this doesn't seem to be true. When we observe young disks like HL tau or older disks like TW Hydra, they look the same in terms of same size of the disk, same location of the rings. There is no evidence for planets being bigger in TW Hydra than the sun. And so this is a challenge. This idea that these are just the precursors of the work that we see them later around. So then the question is, okay, if these are not planets, what can they, these rings and gaps be? And there are two kinds of processes that have been proposed in the literature. One family of processes is related to snowline effects, so mechanisms that affect dust growth. The others are hydrodynamical effects. So,
Morbi, one thing,
yes.
Sorry, you were losing you sometimes, just the voice. Can you maybe check if you're with headphones, just to check that the jack is well inside?
Don't have a microphone here, but
okay, then let's keep going.
Okay, but stop me if you lose me.
If I lose for too long, I stop you. Yeah, sure. Thanks.
Okay, so for instance, Okuzumi et al. In 2016 proposed that IC aggregates are typically fluffy, but when they approach the sublimation line of the corresponding ice, just before sublimating, before going sublimating, they go sintering. And sintering makes this grain more compact, less fluffy, less porous. And so these grains become easier to disrupt. So he predicts that just outside of the sublimation lines, there is a pileup of small grains, and this builds up a bright disk because it increases the opacity of the ring. Another work by Zhang et al. 2015, Ted is a co-author, they even found evidence looking at the spectral index for larger dust inside. So they concluded that maybe these gaps are just due to dust growth associated with lines, which changes the opacity and therefore produces this alternance of gaps and rings. And this mechanism can be real, but these mechanisms, because they concern only the dust abundance, would never explain the meridional circulation observed in the paper. So I don't think this can be a universal explanation. So let's move to what to me looks more promising, which are hydrodynamical effects. First, magnetohydrodynamic. In a number of works in ideal non-MHD, and unveiling that the disks become very strange when you take into account ionization, magnetic effect. We just here refer to the latest of these papers by Riols et al. And this is an image showing the density in a color scale of the gas around the star. And the dark brown means high density of gas, and blue means low density of gas. And then you see here as white lines, the field lines. And what happens is that for some complicated MHD effects, the field lines are not uniform threading the disk, but they are concentrated in beams across the midplane. And so in these regions, the magnetic effects are very strong. And when the magnetic effects are very strong, they cause some gas depletion. So if you look, for instance, at the radial gas density, but we can look at the gas pressure, which tracks the density of the gas, as Ted explained before. Because of this uneven threading of the disk by the magnetic field, you have many pressure bumps. And so the dust, big dust, the smaller dust, is not uniformly distributed, but has peaks and valleys, which creates some opacity transitions. And then if you pass this through a simulator of radiative transfer, this is the disk that comes out. So showing many, many thin rings. And then if you smooth this image, because the size of the beam of ALMA is not infinitely good, then you get really something very similar to what is observed. Another hydrodynamical effect, and this is even more complicated, has been discussed in this paper by Tominaga et al., two papers in 2018 and 2019. This time I forgot to say something. because you see the magnetic field lines are very densely packed on the midplane and more separated on the surface. And because the gas depletion is inversely proportional to the clustering of the field lines, this mechanism depletes gas preferentially on the midplane. So I think it will induce a meridional circulation. Gas is preferentially removed from the midplane than from. So let me go back to this. This time, this instability has nothing to do with the magnetic field. It's just a gravitational instability in a disk that has gas and gas. They call it a two-component viscous gravitational instability. So it's the instability derived from a combination of dust and gas friction, dust-gas friction and gas viscosity. Quite complicated to say, but this is the result. So the surface density of the gas is not normalized to the initial density, doesn't remain like the initial one, but shows peaks and valleys. It's a 10% effect in the gas density. But of course, in the dust density, it's amplified, and this can become an effect of several orders of magnitude. And because the dust goes concentrated on the midplane, I think this instability occurs on the midplane and therefore tends to create this valleys and peaks in the gas on the midplane. So this instability, I think, would also generate a meridional circulation like the one observed by Ted. So in conclusions, because we are running long, let me be clear. I'm not saying that there are no planets in disks or that no gaps are due to planets. Not crazy. There are planets that are far from their star, and we have evidence, for instance, the system H79. When these planets formed, they were in the distant disks. They must have formed beautiful gaps and rings, maybe even cavities. What I'm saying here is that we should be cautious. I warn against a general association that the gap is equal to a. So what I'm saying is that the planets that are deduced, in quote, by observing and modeling their rings do not have yet the same status as those detected by radial velocity or transit, or even microlensing. And so we should be careful not falling into the temptation to declare that all gaps are due to planets. Already the exoplanet community has the tendency to say that most of the super Earths they find are habitable, but we should not fall in this temptation, because I think on the short run, this attracts a lot of press attention. In the long run, I think this will discredit our work. But certainly some gaps. There must be some planets there, but probably we should not be too optimistic in saying that each structure that we see is due to the planet. And then I will stop here and take your questions. Thank you.
Thank you, Morbi. I think this was a great set of two talks, and they were very complementary. And before asking questions myself, which I have quite a few, I will start from Ted. Morbi had the opportunity to counter argument what you said. So now you also have the opportunity to start a dialogue between the two of you. If there is anything specifically of what Morbi mentioned that you would like to address.
So that was really awesome. One thing I wonder is, we worry about making, it's difficult to make the planets via, say, pebble accretion at large distances. But on the other hand, I mean, there's two things. One is we don't know the original mass of material. So there could be substantially more material, and that's just a fact. We have to live with that. It's okay, that helps. But there's the other factor that the dust grains are drifting in, right? You take TW Hydra, right? Its outer radius today is 200 AU in CO and scattered light disk, but the dust disk is at like 60 AU. Now, some of that could be viscous spreading of the gas, but it's pretty clear that the outer disk dust was transported inwards and dumped somewhere. And I wonder if that process itself could induce planet formation in some way.
Oh, for sure. I mean, I'm not saying that planets don't form, but it's much easier closer to the sun, so closer to the star. So you have this global dust drift, and if you are closer to the star, well, you have first a bigger reservoir because you have the entire disk that can feed you. if you are already close to the edge, there is only the dust initially in the ring between the forming planet and the outer edge of the disk. The flux can last for longer, and then you have a number of other properties. The disk is thinner, the orbital frequency is higher, so it becomes much easier. There is a problem in general that although we see evidence for some dust migration, the dust migration doesn't seem to be as fast as theory would predict, as if there are obstacles to dust drift. And well, this has been debated a long time in the literature. Paolo Pinilla, for instance, wrote several papers arguing that, yeah, the disk must have several pressure bumps or mini bumps that look like trapping places or modulate the speed of the grains. But if you have to invoke planet formation to form them, then you have a sort of a chicken and egg problem, right? So you want the dust to stay a long time so that the planet has time to grow, but then you want the growth of the planet in order to create these bumps, in order to preserve the dust and let it stay there for a long time. So this is, to me, is a real chicken and egg problem. So I think that it's very promising, these magneto-hydrodynamical simulations that are done today really show that the disks are not smooth when the interaction with the magnetic field is taken into account. This creates many bumps and this slows down dust drift. Sometimes dust is trapped, then it's released because we don't know if these bumps are fixed structure. They are probably not steady state structures, but come and go. So it's like playing ping pong. So the dust goes, it stops for a while, then it's released, it stopped again. So I think these simulation, magneto-hydrodynamical simulations, can explain the morphology we see, can explain the fact that the dust doesn't drift freely as in a smooth alpha disk. And why not? By piling up dust in some rings, they can favor planet formation. But as I showed from my paper this year, the rings that are distant from the star still don't have enough mass to create to make a Jupiter core. Whereas if I take the same disk, I scale it down to 5 AU, I form a Jupiter core in a few 100,000 years.
Maybe following up on this, I mean, just because it's very related, can I ask you mostly for Ted, since it's mostly observational. For example, in what Marb is saying now, you know, in the B77 ring from D sharp, basically accretion rate from the pebble accretion is linear with the pebble surface density, right? And that it's heavily dependent on the surface density estimates we have from continuum observations. So, and we know that that's actually a fairly difficult measure to obtain because of the possibly very of the high optical thickness of the dust in the radial location. So what's your view on that from the dust point of view, and whether the gas might help on this?
Right. So the trick is that actually the observation is super easy to obtain now that we have ALMA. And the dust, where we have the best sensitivity is to the thermal continuum emission. So that's why we have these gorgeous images with the high resolution. The trick is in our assumptions. And there's several papers out now that are suggesting that the millimeter wave dust emission is optically thick, and we may be seeing actually dust scattering as opposed to tracing the total column of material. And as I noted, you know, if the grains grow, and we need the grains to grow, right? We know in the solar system that large bodies were present within a few 100,000 years after the birth of the solar system. So there are big things there. And for astronomy, big things are centimeter or larger for these observations. So the mass is off. There's lots of data and work that is showing, suggesting that the mass is off. A paper by Carlo Manara a couple years ago can be called out about that. So we could use the gas. The problem is the CO is an imperfect tracer because its abundance is now inferred to be a moving target as well. So we need independent tracers, and the best one we have is hydrogen deuteride. And in the systems where we have observed it and detected it, which is 3, we see evidence that the disks are fairly massive in gas, 0.02 or 0.03 solar masses, which would imply a significant reservoir of solids that was present. If you just divide that mass by 100, and of course there could be mass loss from earlier stages, gas mass loss. So the mass could be even higher than over time, integrated perhaps, than what we're estimating. And so I'm wondering, everything's pointing to me to go to the few 100,000-year-old systems, and what is the mass in those systems? What is the dust structure in those systems, to understand something about what's setting the stage?
And another question that I got from listening to both of you, it's really about when we compare the observations of disk with the mature exoplanet population, we know that disk observations, I mean, you both mentioned this, but they're somehow extremely biased in the sense that the ability to see substructure, we know depends on the linear resolution. So you really need big disks to see gaps and rings, for example. And mostly so far, ALMA in particular has targeted very bright objects with maximum resolution, let's say, of about 20 to 30 milliseconds. And for example, I guess, if you look at these objects here, and you compare the statistics with the whole disk population, let's say they're in the top 20% of the disk distribution. This is part of the distribution of objects that have been detected in the millimeter, but you have many more with infrared excess that still had some kind of disk material. So let's say I'm making up numbers, but 10% of the brightest disks. And so if we were to kind of try debiasing this, how far will it be from the mature exoplanet population in the far out massive planet ranges, where you might in particular mentioned that there is some friction, if you see the point I'm trying to make here.
Yeah, so the comparison, so Ted did this comparison, but he looked at the occurrence rate of giant planets from 1 AU to 100 AU,
yeah,
and some 20% and so on. But most of these planets are closer in, like the warm Jupiters. The planets that are far out are very few, and actually all the expectations of discovery from GPI and Sphere failed because indeed nature doesn't make too many planets far out, or these planets become very faint very quickly, right? Because there is this issue of cold start, hot start. So these planets are seen, they don't reflect the light from the star, are seen from their own light. So when they are still young and warm and bright. So if the planets start relatively cool, or they cool more rapidly, then of course they become invisible sooner, and then you detect less. So there are a number of things in the theory parameters that you can change in order to try to accommodate this. The Pentetal paper makes a nice discussion of this. So they recognize that using the nominal numbers that everybody quotes, they see too many planets, and at distances of 100 AU compared to what the GPI and the Sphere detect. Then maybe if these planets seen in disk are really just 2 Jupiter masses, and rather the planets that we see by direct image are 10 Jupiter masses, and then they become dark relatively fast, well, maybe you can reconcile the two, but it's a little bit stretching a little bit models and parameters. If instead these planets are small and migrate, in terms of numbers, it can be okay. And this is the 20% that Ted invoked, 10% more or less. So we can be within a factor of 2, difficult to rule it out. My point is really that we should see these rings moving and becomes broader and more sharp as the planet is growing and migrating. So, and I think we don't see any clear evolutionary pattern, and Ted can correct me if if I'm wrong, of course.
We don't have the data set yet. You know, these observations are time consuming, even for the dust, and the duty cycle for AMBA is very slow. So the systemic data are not there for structure versus time. It's very different.
If we see some evolutionary trend in the future, that of course will support enormously the idea that our planets starting to grow further out and then growing and migrating in. No doubt.
Yeah, I mean, it's important to state that the maximal interpretation is actually mostly planets that are lower mass than the detection limits, right? So we're probing a space that is unconstrained observation. They were difficult to constrain, but I take Morby's point, and we talked about this in Rich and Jehan and I, that, you know, we need to detect one of these planets directly to sort of help us calibrate what we're doing in the millimeter. We're pushing an instrument in a new way, and it's very exciting, but we eagerly await James Webb and its ability to hopefully constrain planets at smaller masses at greater distances when they're young.
Yeah, because maybe it's good to remind to the audience that we do know some planets in disks like PDS 70,
Yeah.
but totally different. Well, Ted showed the image. They are not in a gap between two rings. They are inside at the border of a big cavity.
Yeah, the transition disks are example. And the Villeneuve paper on Sphere, I think, was talking about transition disks for those who were interested.
Yeah, there is no doubt there.
So we have questions flowing, and many of the ones I'm receiving are actually related to MHD effects. And I would, so good luck. And but but they're very general. So I have two which are very coupled, and I think they're for both of you from observational and theoretical side. So one of them is really what kind of magnitude do you need, order of magnitude do you need, and for the magnetic fields to really be able to generate these gaps that you would see in the observations. And on the other side instead is from the observational point of view, do we think that the ionization fraction we see, which is extremely challenging to observe, but let's say if the ionization structure we see is sufficient to basically have the magnetic field being well coupled to the hydro of the gas. So these are the two simulations on the questions on MHD effects. So okay. I don't know who wants to start, Morbi. Okay.
So on the value of the magnetic field, I don't remember. And also then it changes because the magnetic field can accumulate a specific location. But what I know, without knowing the exact numbers in terms of nanotesla or whatever, is that there is a paleomagnetic field recorded in meteorites. And for meteorites that form in the first 3-4 million years. And the intensity of a magnetic field that is measured is in line with what is invoked in this kind of MHD simulations. So these simulations don't use crazy fields, which are unrealistic. They actually use the fields that are supposed to exist in interstellar medium.
So there he goes. He did it. He pulled observations out in an area where we don't have observations, and he's absolutely right that the meteorites is the best constraint that we have. The ion fraction is tricky. The big question that we have is whether cosmic rays are present in the system or not. Cosmic rays are the things that have the greatest penetrating power to get down to the midplane and ionize the midplane. And we need the midplane to be ionized to couple for the magnetic. The ions are trapped with that field, and collisions with H2 would then communicate what's happening with the field to the gas, and then that would transfer to the dust. So this is absolutely a very important question. In our solar system, the cosmic rays are kept out by the solar wind, the ones responsible for ionization. And in the one disk where we have tried to estimate at TW Hydra, we find that they are reduced in magnitude. That is, the cosmic rays are impeded, which would lower the ionization fraction. Now, I have not circled back to know what that implies for the coupling, but we are working with a student of Xiaowan Zhu from UNLV that is looking at the observations and what they mean. So I'd say the jury is out. And I wrote that down. I was like, well, if the field is strong enough, would you see, for example, would HCO plus trace the gaps or the rings, depending upon what the magnetic field is doing? And maybe that's an area to start and look at.
And related to this, another question is, what can observationally, what can distinguish between gaps created by planets and the ones created by MHD effects, to try to focus the question a bit more? For example, whether we expect that, for example, the ring spacings might differ in the two cases, or kinematically, since we talked a lot about kinematics, what's really the diagnostic which should follow up with future observations to distinguish?
We're at the frontier. There's a lot of interest in what's going on here, but the simulations are we're gonna have to closely couple to the observers and make those predictions. Right now, when we were publishing our kinetical work, it was basically, we had Jehan doing all the analysis, and when we were trying to compare to observations in the literature or predictions from other models, there weren't enough happening, enough predictions at large distances. So you saw the paper that Morby showed is very recent. And so we're on the cusp of doing this work, and so that's great. It makes it exciting.
Morby, you want to comment?
No, there is not much to add. So indeed, the MHD people should try to see what kind of meridional circulation there is, if any, and compare with that a planet creates. Compare that. If there are planets, eventually we should find some direct evidence for these planets. So seeing the gap and the kink would actually help, and we've seen this is the case in some of the Pence paper. So, something like that.
I mean, I could say that, we measured the kinematics from 12 CO, which would be emitting from up here. And we're at the stage to try to look at it from 13 CO, which is, so if this is the midplane, 12 COs up here, we have the data now for 13 CO, and we're looking to see, well, does anything change in the kinematics? And can we go even deeper with C18O? And that will provide the data to then compare to models. And so we're getting there.
So maybe final two questions. One is if both of you could comment on something that hasn't been mentioned too much, but there are observations, in particular in the dust continuum from ALMA, but also from scatter light images that show not axisymmetric structures, like this kind of maybe vortices, or let's call them these crescent-like structures. Are those maybe a preferable diagnostic to distinguish between MHD or some hydro instability versus the planet scenario?
Well, the transition disks, and so the vortex that is at the edge of the cavity, is probably due to some to planet formation or formation of secondary, companion. That's much more reliable to me for the moment than the gaps and rings. And some of these structures, asymmetric structures that we see are in scatter lights, so one has to worry about shadowing effects from the inner part of the ring, which may be misaligned, and you know a lot about this, of course. So not everything is genuinely in asymmetry due to a perturbation from a planet or a companion star. So things have to be looked on a case-to-case basis. But I would say that there are a number of transition disks, and it's very appealing that a transition disk should have a giant planet just inside of the edge. And what we see for PDS 70, it's exactly that. And we think that the solar system, when Jupiter and Saturn formed, eventually became a transition disk, and we see evidences of that in the meteoritical collection, because inner solar system meteorites are made of a dust, which is totally different from the outer solar system meteorites, showing that the dust didn't pass. And so I think that is really, really solid. And even if the planets are not always found, we will find them.
Yeah, I think that it's an excellent point that there's other things that are not asymmetric, you know, besides the rings and gaps. And you could talk about the, you know, the vortices and, you know, what causes the vortices. That's an important scientific question to explore, and whether planets are related to that. Spiral structure. We see spirals in some of those continuum data. Do we see similar spirals in the gas? What's causing that spiral structure, right? That also is an area that needs focus. And indeed, people are certainly working on it. So it's not just the rings and gaps, it's all of the above at getting at this very important question.
For the spirals, though, we are probably talking of objects which are more massive than planets. Very strong structures.
So actually, I think the kind of answered already to what I picked as the last question. And I think we are above the 1 hour and 30 minutes already. So I think we can actually conclude here. And first of all, I would really like to thank both of you, Ted and Morbi. I think this has been great, and I loved it, and I learned a lot. And I'll contact you since I have other ideas that came up during the discussion, of course, which is what is great about this kind of talk series. And unfortunately, people cannot unmute and applause, but I will do for them. And so with this, I'll conclude. I think, again, this was great, and it showed how much there is still to do on this particular field of astronomy and astrophysics. And therefore, personally, I'm very excited to be working in this particular topic for my research. And so I'm really looking forward to discover more and more what's at the origin of these substructures that we see. And with this, I'll conclude. Giacomo, do you want to say anything in particular?
Yeah, no, just to, from my side, also want to thank the three of you, also you, Stefano, and Ted, and once again, thanks to Morbi for the participation. I see a lot of people also thanking from the chat, I can tell you. There was a very lively participation. Thank you also for the people who sent the questions, and maybe just to make, reinforce the concept that we will take all the questions, that then we'll send it to the speakers, and we will collect the answer, and we will put together into a short booklet that you can take, and then you can see, as I said, the follow-up of the questions that were made. Some of them were answered. Maybe if there is more pending, that everything will be on PDF. Also, the presentation will be online, and so it can be seen and seen again. This is a big legacy for the next 10 years of observation, in fact. So let's see, we can watch it back in 10 years and see. But thank you very much. It was really inspiring. And just concludes by saying that there will be another duologue next Monday, in fact, about dust at high redshift. So please stay tuned. We will send around information. You can subscribe to the channel, and then you will get a notification automatically. With this, I conclude this as well, and I thank you everyone, and have a nice day. Bye.
Okay.
Thanks again.
Thanks to you. Bye-bye.
Thank you. Bye. Bye-bye.